We've been doing a lot of implicit differentiation in this section. That's the title of the section, not surprising. And so we're going to take a look at a power rule again. And the reason this gets sort of rolled out in different phases has to do with the proving of it throughout the different sections in the book. So what we're going to do is we're going to prove the power rule, but this time what we're talking about is for rational powers. So this is our power rule, and we're going to prove it for rational exponents. So what we want to do is we want to start off and say, okay, let's let n, that power, be a ratio of p over q, so a fraction, where p and q are integers. So where p and q are integers. So that's the definition of a rational exponent. It can be written in the form of an integer divided by an integer. All right, so now if I am, so then let's then also say, and I guess I'll say that, let's also then start off and say, let's let y equal x to the n. Okay, so y is equal to x to the n. All right, well, that's going to imply, based on the fact I'm saying n is a rational exponent, that it can be written as a ratio of this p over q. So what I'm going to do is I'm going to exponentiate both sides here, raise both sides to the power of q. So on the left-hand side, we now have our y to the q. Actually, I'm going to not write it in a row. I'm going to write it beneath it. A little easier maybe to follow. So y to the q. On the right-hand side, powers to powers we multiply, and that's just going to give us the x to the p. Now what I want us to do, so we haven't done any differentiating here, but we've gotten it into the form that each side is written as a base to an integer exponent, and we have shown the power rule for integer exponents, both positive and negative at this point. So we're going to differentiate both sides with respect to x, and we're going to be using our implicit differentiation. Because on the left-hand side, when we're differentiating this y, yes, we're using power rule, so q, y to the q minus 1, but I just differentiated a y, so I have to introduce this factor of dy dx. Now, on the right-hand side, it's just differentiating a factor that is an x, so I can just apply the power rule, so px to the p minus 1 power. Now what we're going to do, just like what we always do with our implicit differentiation, is the next step is to solve for dy dx. So we are going to divide both sides by q, y to the q minus 1 power. So on the left-hand side, I have now isolated for my dy dx. And on the right-hand side, let's start to see if we can clean this up a bit. So I'm going to kind of break off in front the p over q. And I like the look, of course, of, x here. That's fine, to the p minus 1. But I'd like to get this derivative entirely in terms of x. And here's what I know. I know that y was originally equal to x to the p over q power. So I am going to replace the y with x to the p over q power. So we knew from the beginning here, y was equal to x to the p over q. So I am replacing y with x to the p over q. Now, of course, that whole thing is raised to the q minus 1 power. So that's what we have there. Now, powers to powers we multiply. So I would, in this denominator, I'm just going to kind of write this off to the side here. I would think of that p over q times q is just going to be p, and then p over q times the minus 1 is a minus p over q. So that's the factor that we have in the denominator. And then if we think about dividing with the same base, that is when we subtract our exponents. So I would now have x to the numerator exponent is p minus 1 minus the denominator exponent is the quantity of p minus p over q. Well, what does that whole exponent work out to be? Let's distribute through that negative, so we'd have a minus p and a plus p over q. And of course, your two p's there are going to go to 0. And so what we now have is we have that dy dx, so our derivative of x to the n, is equal to p over q times x to the, and I have now simplified that exponent to the form of p over q and a minus 1. And p over q is what n is. So this is n x to the n minus 1. So we have now shown that the power rule holds for rational exponents. Now, I mentioned early on, this is kind of unique in this book, this rolling out of the different proofs along the way, and then they roll out in the homework as well, and I don't dislike it. A lot of books just immediately start with examples like right from the get-go that would have involved rational exponents, and they just sometimes put the proofs in the appendices, or they say proofs to follow later or something like that. So in this section, you're going to have lots of implicit differentiation homework problems, but then in the midst of all of this, you're going to see just some basic power rule questions, and it may feel like a little bit of an odd fit to you, but the whole reason is because they were now able to prove the power rule for rational exponents using, up above, what did I just use? I used implicit differentiation. Okay, so now we're just going to look at exactly that. A couple of examples. It's just power rule, but it's working with rational exponents, which of course are radicals. So one of the things that I would say kind of off to the side here that you need to recall is that, and I write this only from years of teaching where students have often forgot working with radicals and rational exponents. So the most basic radical that you ever work with is your square root. Hopefully that one is the one you know super well, is just being x to the 1/2. One level up, generalizing the nth root. The square root, think you're even saying it, square root, is the implied index of 2. If there is a different index written, that of course is your denominator of your rational exponent. And then the other kind of extension above that is if there is a power either outside of the radical, let's say here, or it can also be inside of the radical, provided that it's the entire inside of the radical being raised to that power. But this is x to the m over n. So you need to remember this course, one of the things that students sometimes do struggle with are the basics of moving in between rational exponents and radicals, and then sometimes they confuse that with negative exponents, so we need to make sure we're able to do these things efficiently here. All right, so this first one that we have up here is not ready for differentiation yet. I need to get these as x's to powers. So the first one here, the square root of x cubed, that is x to the 3/2 power. And you really want to be able to think of it that way. Sometimes students will write it initially as x to the 3rd raised to the 1/2. That's okay, but then make sure you realize that's x to the 3/2. What I don't want you doing is taking derivatives and applying chain rules and doing all this stuff. I will see students do that. Then they leave it as x cubed to the 1/2 and they apply a chain rule. It's not that it's wrong, at least they remember chain rule, but it's so much more work and the answer is more to simplify. So we don't want to have to do that. So if you have to first say x cubed to the 1/2, okay, but realize that's x to the 3/2. Okay, now, same thing here. Let's get into our second term. In the denominator, this is really so what do I really have here? I have this minus 9. I'll leave it in the denominator for right now. And the cube root of x squared, well, that's now kind of the exact opposite of what we had in the first term. That's now x to the 2/3. Again, if you have to first think of it as x squared raised to the 1/3, that's okay, but then write that, multiply those together, it's x to the 2/3. Now this still isn't in the form that I want for differentiation purposes, because I don't want to have to do quotient rule on that second term. And right now, if I leave it like it is, when I get to the second term and have to take its derivative, I'd have to use quotient rule. So let's bring up that x to the 2/3 into the numerator and write it as x to the negative 2/3. I would also strongly encourage you to not start taking derivatives of like the first term while you're still rewriting the original form of the second term. That often happens with students, and then they, will make mistakes. They forget to take a derivative of a particular term or something. Okay, so this is now in a form that is what I would call ready for differentiating. So just basic power rules. So you're bringing down the 3/2, and of course you're going to be able to reduce your 2's, and then x to the 3/2 minus 1. So 3/2 minus 2/2, that's going to be 1/2. Then minus your 9/2 times, you're bringing down your negative 2/3. And of course, that's going to change that to addition. Yes, you're going to be able to do all sorts of reducing. Hopefully you can do some of that in your head. And then x to the negative 2/3 minus 1. So negative 2/3 minus 3/3 would be negative 5/3. And then the derivative of a constant goes to 0. So what do we have here if we maybe rewrite this, clean this up a bit? We have our 3x to the 1/2. And then we have our plus 3x to the negative 5/3. That, of course, is mathematically correct. You can leave it that way. If you really wanted to rewrite it with a radical, let's do that just for practice. That's 3 square root of x. And in the second term, I could move that into the denominator where it's x to the positive 5/3. And then x to the positive 5/3 would be like the cube root of x to the 5th, where that 5 could either be inside or outside of the radical. And again, you wouldn't have to rewrite that radical form of the answer, but I just want us to get more and more efficient at moving in between those forms. Most importantly, I think, is being able to rewrite the original radicals that we had as their most simplified form of those rational exponents. Makes the derivative easier. All right, so let's take a look at one more example here. So number 2, again, we're just working with this here. And so the radical exponents that come from radicals. So let's say we had x over, and let's say we just had a basic square root of, in the denominator, x squared plus 2. So at this point, anytime you start seeing your radicals, in order to take the derivatives, you're going to definitely need to be thinking of rewriting these as their appropriate rational exponents. So here, 1/2 power. Now, I would leave that one just like it is. I wouldn't bring it up in the numerator as the x squared plus 2 to the negative 1/2. All you're going to do is rewrite a quotient rule situation into a product rule situation, but now a product rule with negative exponents, which eventually, when you need to be able to simplify, you're going to want it out of negative exponents anyway. But that's really a personal preference. It would be mathematically correct to do so. All right, so let's go ahead and jump into our derivative. So we know that with the quotient rule, we always start with our original denominator, which I'm just going to leave as the square root since I'm just rewriting it. So the original denominator, quantity squared, which you might recognize is just going to be the binomial x squared plus 2. That's my prompt to start with my original denominator left alone as the first part of my first term, and then times the derivative of my numerator, and of course derivative of x is just 1 here, minus, and now changing that order, so now it's going to be the numerator left alone, times, and now the derivative of the denominator, that's really where I need to be looking at it as that quantity to the 1/2 power, because this now requires chain rule. So the derivative of the outside is going to be 1/2 inside left alone to the 1/2 minus 1 is going to be to the negative 1/2 power. But again, this is with the inside left alone. So with our x squared plus 2 left alone. But that is now my inside. Oops, oh gosh darn it. Oh good, I was able to bring it back. I meant to hit the highlighter, I do that all the time. So there's my inside. Now I need times the derivative of that inside by chain rule, so times a 2x. So this whole quantity here represents the derivative of my denominator. So there's the derivative. Now, I want us to simplify this a little bit, especially the further we go in this course, the more you're going to need to be able to simplify. So would your homework maybe take some horrific mathematical equivalent if you entered it correctly? Sure. At minimum, I'd say let's at least clean it up a bit, make our even just data entry if I'm entering the answer into an online program easier. So what can I do in my second term here? Well, I can do a couple of things, right? I mean, I can, at minimum, I can reduce those little 2's. That's exciting. I can multiply the monomial portion. The x times the x is going to give me an x squared. And the first step for me in any simplification process is to rewrite negative exponents and so that they are positive exponents. So that means moving and creating a little mini fraction there where the x squared plus 2 is in the denominator to the 1/2 power. It can't drop down into the primary denominator because you have that big subtraction sign. So it has to create its own little mini fraction there. Now, I mean, at least that's cleaned up. That would at least be easier even just to enter as an answer and just to kind of look at it. It looks a lot nicer. So once again, I'm going to do what I like to do to get rid of complex fractions, my kind of preferred way to do this, which by the way, now that it is a 1/2 power, you know, maybe we could just think of this instead of a 1/2 power if you prefer. Again, this is kind of a personal preference. You could now think of it as a square root. So I am going to multiply as a big version of 1 here by that little mini denominator of the square root of x squared plus 2 over itself. And again, I could have left these as 1/2 powers the whole time. I think it, once again, 1/2 power square root. Personal preference, you really want to be able to just move in between them really efficiently. So what do I now have for my f prime? Square root of x squared plus 2 times itself is just going to be x squared plus 2. In the second term, the square roots reduce, one in numerator, one in denominator. And now in my denominator, let's recognize I'm really multiplying with the same base. I mean, you could leave it as x squared plus 2 times x times the square root of x squared plus 2. But if you think of the square root of x squared plus 2 as really just being a 1/2 power, you could also then rewrite that, multiplying with the same base, you're adding your exponents. So it would be to the 1 1/2 or the 3/2 power. You would never write 1 1/2. And the numerator is now just simplified to 2. So this would be a nice simplified form of that derivative. All right, so we'll go ahead and end here. Next time we're going to look at just a short little rule for the absolute value of a function.